We're going to talk about is we're going to talk about this phrasing that's come up here and there, normalization. And this is related directly to the idea of these anomalies and trying to eliminate these anomalies in your database. Because when you think about it, you have to think, what does my database contain? Does it contain data or does it contain facts? If it contains data and I'm just querying that data, then I want those queries to be easy to write. I want them to require as little mechanism as possible. I want the data to be really easy to retrieve, so I want it to be, co-located in memory. And so I kind of want these really wide, really simple single table design. That's what makes it easiest to store raw, just dumps of data. But if I want to contain facts about the world, and I want those facts to be correct, and I want them to be correct over a period of time, and I want to be able to assure myself that this can only contain correct facts, then I need a different design. And this is where we have designs with multiple tables, where the tables are have far fewer columns. And there is a particular piece of theory that I want to share with you about how we design. And this is what we call normalization. Surprisingly enough, the term normalization came up in the 60s. It was based off of, if anybody remembers, Nixon normalizing relations with China at the time, and they said, why don't we normalize the relations in our databases? What that means is sometimes hard for us to grasp. And if we look at the different normal forms, we'll often see people refer to them in terms of primary keys, in terms of prime attributes, atomic columns. You'll see people say things like every non-trivial functional dependency either does not begin with a proper subset of a candidate key or it ends with a prime attribute. And who knows what that even means. And so what I want to share with you is a very simple exercise walking through the normal forms with a before and after. And each step along the way, we can identify how we have eliminated the possibility for an anomaly. We'll only go through the first 3 normal forms. There are many more normal forms than that. You may have heard of 4th, 5th, 6th normal form, Boyce-Codd normal form. There's all sorts of these. We'll look at the first 3 where you get quite a bit of bang for your buck. The remainders, I won't say are useless. They're useful, but they do introduce very, very, very small tables, very complex queries, and you might argue that maybe those might be no longer providing the most immediate benefit, or at least the greatest degree of benefit for your use case. In the first normal form, what we're going to do is we're going to add a primary key, and we're going to make sure that we store only atomic values. And so in order to construct something where that doesn't match, here you can see I have a table. It doesn't have a primary key, whatever that is, and it doesn't contain atomic values. Here I'm storing some sort of physical hardware, some entity, and some components that this hardware has. So if this is maybe a physical device in a data center, these components may be the subcomponents of the device, the motherboard, the optics card, the Ethernet switch, or they might be things like the ports on the device, something that I want to store data against. And each one of these rows no longer contains single entities. As a consequence, I can't do things like, store values for the single entities, and it's going to be very tricky if I have some measurement that I want to store. And so, in the first normal form, we're really not asking a lot. We're just storing each individual atomic piece of data separately. We're saying each row is an entity and component, and we're making this a primary key. We're making this a unique entry. And so, in this database, we can no longer store anything that isn't a unique entity component tuple. So we're guaranteed that the entity might not be unique, the component may not be unique, but the combination of the two are unique, and any value we store associated with this is the only one value referring to that one unique atomic entity. Not that difficult. Now, there may be something that we might do mechanically that's a little bit beyond this. Instead of having the primary key be the actual entity and component names, the textual, the string names for them, we might make this an identifier, just a numerical identifier, and we might have a uniqueness constraint. So in practice, you might say, the entity component names, maybe I just want to have a unique identifier and use that as a non-natural primary key. Sometimes people say, your primary key, should it be a natural primary key? Should it be a primary key that's directly derived from the data? Or should it be something that's not directly derived from the data? And this is where it gets kind of tricky, because every time I've been in a situation where I ask somebody, is this field unique and unchanging? And the unique singular way to refer to this thing, I get conflicting answers. We even did this. We did a session on SQL last year. And in that session, we had somebody who was an expert on physical hardware in data centers. And we asked them, is the model serial number unique? And they said, well, there are circumstances where it's not. Is the host name for this device unique? Well, host names change all the time. And we kept asking questions, and I say, well, you know what? Burned into the EEPROM is a unique serial number identifier that cannot be changed because it's in write-only memory, except sometimes when we RMA the devices, they replace that one component, and the entity itself that we consider to be the same entity has that thing changed. And in a case like that, maybe we want some sort of synthetic primary key. We want some internal identifier that we then map to the external identifier, because we can never really ensure that that external identifier here is the unique entity. And so there might be some more complexity to this first normal form, really deciding what is the unique entity. Is it something that we track internally, like just an ID of some sort that we map to an external thing, or can it be part of the data that we got, like a model number or a part number or a serial number, if we're really certain that those things don't change? In many cases, we can make that assumption, but Social Security numbers in the United States can change. You can get a new Social Security number if you want. Combinations of birthdays and names, well, names can change. Birthdays, I guess, can't change. I don't know. Maybe they can. Maybe you were born on the 30th of February, and then somebody later on realizes, hold on a second, that doesn't exist. We got to change all of your records. There may be cases where you want a synthetic primary key instead of a natural primary key. In the second normal form, you're removing columns which do not depend on the entire primary key, because those tuples where they have those extra columns that do depend on, or that don't depend on the entire primary key, lead to these anomalies. So here's an example. Here I have an entity, a component, some value that I've captured for that, and some information about this entity, the model and its manufacturer. And when you think about it, the value depends directly on the primary key. Whether we consider that to be this ID column or this thing, we're going to say this is some measurement that we captured for this unique entity. So that directly depends on the primary key. The model number directly depends on the primary key as well, because the primary key directly determines what the model number is. But the manufacturer doesn't, because the manufacturer depends on kind of the model number, right? Which depends on this. And even then, you might think that these two columns don't really depend on the whole primary key. They may depend on just the entity itself, or they may not depend on, the entity and the component. And so, as a consequence, what you might say is, oh, we actually have the case where these two columns might only depend on a portion of the primary key, or this column really doesn't depend directly on the primary key, or it depends on the primary key in some transitive fashion. And so, what we could think is, if it's the case that these two pieces depend on just the entity itself, then a change here may not be reflected as a change here, and you have an update anomaly. This is a case where you could accidentally change the model for, here, I guess what the model number is referring to is the component. So you could change the model name for this component, but it doesn't change for this component, and you have an anomaly. And so in the after case, we're going to split this up. We're going to split this up into two tables, and we're going to have a foreign key linking these two tables. In the first table, we'll have the models and the manufacturers. And in the second table, we'll have the entities, the components, the values associated with them, and some identifier for the model. And so here you can see, okay, the model is now in this modeling determined by the entity and the component. But we could also, determine this based off of the component itself. We could do something like, create another table for the components. And we could say this is actually stored against the unique component. And do something like this. And then link that in. And so really depends on which our modeling is. Either one might be, realistic to see in our use case, but fundamentally in the second normal form, we're trying to eliminate these very basic anomalies. And I think you can see it's not asking a whole lot, and it's really worthwhile doing this because you can eliminate some very trivial anomalies. However, the query to actually get the results of the data that look like what it started with is now a little bit harder because we have to do a join. So this may also necessitate the use of some sort of view or some materialized view. In the third normal form, we're looking to remove columns with transitive dependencies. So we're looking to remove columns where that column depends on something which depends on the primary key. And so again, in this before modeling, we can see we have each entity component value combination. We have each model manufacturer combination. And in this particular use case, what we can imagine is the model number is related to, or for the primary key here, which is just the unique identifier for the model, we have a name associated with it, and then tied to that name, we have some manufacturer. Again, we have update anomalies where a change in one place won't cascade to the change in the other place, and so we decompose that, and we end up with something like this, where we break this down into the data, the models, and the entities. And what you can see with these normal forms is we're effectively trying to break down a table that's containing too much information, where a change in one place, an insert could lead to a conflict in terms of what is the correct fact. A delete could remove data that is only stored in that row, or an update could update something in an incorrect fashion, could update it here but not update it everywhere else. Well, all of those are risks that we have that could lead to this data being incorrect. And the normalization process is really about identifying what is the unique way to refer to this row, where there can only be one row, and what are the keys, or what are the data associated directly with that. And as you go deeper into these normalization, you're really just trimming down the number of columns you have until you end up with really small tables with just one key and one column. That might be going a little bit too far, but where you can eliminate some of these. Now, obviously, another thing that you might think about here is whenever you break this into other tables, part of what you want to keep in mind is, am I tracking a one-to-many, many-to-many, or many-to-one relationship? And in the one big giant table possibility, it's very difficult for you to ensure that you don't have those kind of duplicates, that you're really ensuring that this is a many-to-one relationship or a one-to-one relationship or a one-to-many relationship. Whereas as you break down these tables in this normalization approach, you can structure the tables in such a fashion where you can model this one-to-many or many-to-one by making one of these columns unique. Think about it. If you're linking two tables together, and on one of those tables you mark one of the columns that refer to the other table as unique, then you've made this a one-to-many relationship. And if you have a dual linkage, you could make the dual linkage a one-to-one relationship and a central linking table. Here you can see something like this. The entity and the model are via some table that only contains the linkage itself, which has its own primary key that refers to the linkage but is not really ever used anywhere. And that ensures this is a one-to-one relationship. And so you also get the ability to constrain those types of relationships to make sure the data is correct. Unfortunately, however, you do end up with more joins and more complex queries. And so again, it is the case that as you start to do these decompositions to third normal form or Boyce-Codd normal form, and usually I stop around Boyce-Codd or fourth normal form, or actually usually stop about Boyce-Codd normal form, you do end up needing maybe some sort of view or materialized view or some sort of trigger just to make sure that you can also do really simple analytical queries. Because people like to just do a single select. Joins can be a little bit clumsy for people, and the exact, is it a left join, is it a right join, is it an inner join, may sometimes require them to think a little bit harder than they want to think. And so you can store the data factually correct and then provide them with a view that says, hey, by the way, if you're joining this information together, I've done it for you already. Just use my view and move on with your life.